Start. Okay. So module four, as you can see here, is going to be acceleration analysis. And this is going to be chapter 7 in our book. If we go to module 4 learning plan, you're going to notice that there are 2 PowerPoint presentations. We're going to be looking at the first one this evening, and then the next time that we get together, we'll look at the second one. So I am going to, and might as well, it's worth kind of taking a peek at. You'll notice that we do have practice problems and assignment number 4. I want to point out that the things that we're going to be doing here in class are going to be the items that we're going to be submitting for our practice problems. And I notice, oh, they're mislabeled. So let me make that correction here really quickly. Let me just pause the video for a second. Okay, so I just wanted to fix this up. We are going to be doing the first 3 examples this evening to kind of get started with the subject of acceleration. And then the next time that we're together, we'll continue on and do the last problems that we see here. So going back to Module 4 learning plan and pulling up the PowerPoint presentation, part 1 for Chapter 7, we are going to get started. So if you did want to open up your book, chapter 7 starts on page 170, and we will be, referencing the items that are in there. So acceleration analysis. Now, I was going to take a look, but I think we've seen this in another class. So this was just a reminder. If you remember from Despicable Me, there's that cute kid. I don't know if he's cute. He's a villain. Yeah. He's not cute. He's a villain, but his name is Vector. And I just think it's cute because he, when my kids were young and I watched this, I just had a chuckle because I'm like, Vector, he has both magnitude and direction. So if you're familiar with it, if you're not, take a look, but I'm not going to take time here in class to do that. But what I did want you to do is, as we're going to be looking more and more, and we're going to continue to look at vectors, I'd like you to just make a short list. I'm going to give you a minute to write down all the ways that you encounter vectors like every day, on an everyday basis. Where are vectors around you in everyday life? And we're going to generate a list together, if you would. Sounds like it's really fun to be next door sometimes, doesn't it? I don't know if those who are virtual can hear it, but you really can. What was that? I don't know if they're having a party, but man, there's a whole lot of fun going on over there. What do you mean, why aren't we? We are having fun. It's just a different, more serious kind of fun. And I'll get our chat out. So I'll give you a little bit more time to write down places that you encounter or things that you encounter that during the day, like everyday life, that are vectors, that are vector quantities. Need two things to fully define them: magnitude and direction. All right, why don't we start generating our list here? Does anybody want to suggest one, whether you're virtual or in the room? Start writing down. Number 1. You guys driving in a car? Yeah. How? Tell me. Tell me how it's a vector. Driving in a car is a vector. It's accelerating in a direction. So accelerating. Accelerating in a car. Okay. Lex, she has sports things like throwing a ball. Well, how is throwing a ball a vector? Direction and magnitude of a trajectory. Okay, so the trajectory of throwing a ball. Awesome. Then I'm going to go back to Chris's number 3. He has when I hammer a chisel, hitting me hitting a chisel, me hitting. It is the magnitude and the point at the end of the chisel in a direction. Yeah. Yep. Chisel, hammer, force. Okay. All right. Others. Josh.
Going around the curve, like when you're driving.
Yes. Yes. So that would be it's acceleration. Yep, changing of the direction, going around a curve. Gravity would be another one. And Daniel, I'm getting to you. So gravity was mentioned. Number 6, wind. Absolutely. We can feel the force wind, right? Coming from a direct. Oh my gosh, plants growing. Oh, I don't know.
Maybe bamboo.
Bamboo, they go pretty, yeah, I mean, yeah, they would be going in a direction. I think we could make a case for that, Aaliyah. An electrical circuit. Oh my gosh. Yeah, I guess. I remember way back when I had electrical classes, we did use vectors for current. I literally, I don't know how you guys feel about electricity classes, but they're the worst. Ugh. Yeah. Sorry for those who love electricity. There might be some. I know I do love electricity because when you don't have it, you're like, crap, that stinks, but I don't either. I don't either. How about lifting a heavy object? Absolutely. Exert a force, a magnitude to move that object in a direction. Yes. So lifting. What else? Anything else? Friction. Yes, friction is a vector quantity. It's a force and it's going to oppose impending motion. Christian. Okay, a normal force in terms of what on in everyday life. Everyday life. Like what would the normal force be? Oh, that way. Yeah. Well, we're gonna find, yeah, normal force.
Well,
Do we have an 11th one? Does anybody else have anything? Pressure is a vector quantity. Yes. Yeah, excellent. So today we're gonna be looking at vectors, but our vectors are going to still be building on some velocity stuff, but most importantly, we're gonna be focusing, as we said earlier, on acceleration. I anticipate based on how you described things that these items you've probably noticed, you've probably discussed, or even talked about in physics, right? We know that our courses, for the most part, are an application of physics, so we see bits and pieces of that. So acceleration in this particular module is going to be, one of those examples as well. So let me get back to my PowerPoint presentation. So we wrote down a bunch of things that would be vector quantities. Excellent. So today we're going to explore acceleration as it pertains to a single rotating link. If you remember how we divided up our velocity chapter, we're kind of doing the same thing here. We first started with a single link rotating with velocity, and now we're going to do that very same thing with acceleration, and then we're going to build on that the next time we get together, and then start doing some other, I don't want to say more complex, but things that build on that. So our objectives here for this chapter are to, number 1, define linear, rotational, angular, normal, and tangential accelerations. Also use the relative acceleration method to graphically determine the acceleration of a point on a link, and then also use relative acceleration method to graphically determine the acceleration of a point of interest on a floating link as well. So those are kind of our 3 goals for this particular module. So in the introduction here, In chapter 7, acceleration analysis is going to involve determining the amount that a certain point on a link or a mechanism either speeds up or slows down. Okay. All of you, I think, are, well, most of you are either in physics right now or have taken it previous to this. It's part of the, the sequence of things. So I am certain that you have had discussions and looks at acceleration. So acceleration is when we are speeding up or slowing down. Now, an inertia force is proportional to the acceleration imposed on a body. Now, in kinematics, we do not discuss or take into account inertia forces, but we will in dynamics. But we're going to be looking just at the motion side of things. So what we need to do is make sure that we have our motion right before adding the forces then a little bit later, because they are important. Now, when we first start our discussions about acceleration, it's worth kind of backing up, and rather than just looking at a rotating link, let's look at linear acceleration. Linear acceleration is going to be the change in linear velocity. Linear velocity, we know, is the symbol V, okay? Linear acceleration is going to be the letter, lowercase letter A, okay? Now, acceleration, as we said earlier, is a vector quantity. Okay. Now, acceleration directions. Acceleration is going to be in the same direction as motion, as velocity, if that point is speeding up. Okay. But acceleration will be in the opposite direction, pointing in the opposite direction, if the velocity seems to be slowing down. So what that means is, like, when we come to a stop, for instance, and we're driving down the road, if we're slowing down, our acceleration is decreasing, okay? So that means that the vector we're going to find is going to point in the opposite direction. We're still moving, if you would, forward, but the direction of the acceleration or the deceleration would actually be pointing, back towards us, if you would. If we're accelerating, if we're speeding up, then that means that if our motion is, for instance, going straight ahead, that means that our acceleration is helping us in that direction as well. Okay. So by the words speeding up, slowing down, decelerating, accelerating, that lets us know, and it gives us a hint on, in relationship to the velocity, which way our acceleration is going to be going. Now, there's a couple equations on acceleration. And again, these should be familiar to you. And we're going to be looking at equation 7.3, which is at the bottom of page 170, and equation 7.5, which is at the top of page 171. So we'll look at 7.3 first. So down here at the bottom of our second column on page 170, this is our, if you would, kind of standard accepted equation for acceleration. So acceleration is going to be equal to the change in velocity divided by a change in time, or how much does our velocity change over a known duration of time that it took us to do that. Now, many times we are going to expand out our velocity to be final velocity minus initial velocity. So what we need to do is we need to know and understand, are we starting from rest or are we starting with an initial? So a problem will let you know that, but many times, if it's not given, we usually assume that we're starting from rest. Okay, so that means that our initial velocity would be 0. Okay, and our final velocity would be whatever the values, would be given. And then again, how much time it takes us to get there. Now, the other equation that we're going to be looking at is going to be the distance that's covered during a time that we're accelerating. I'm going to kind of get rid of my little notes here. In this book, as we've stated, they call distance capital R for some reason. I'm not exactly sure why, but I tend to replace that with D is just a regular distance. So D is equal to 1/2 acceleration times time squared, the time duration that we're looking at, squared, plus if we do have an initial velocity, we're going to put that value in there times the time that we're speaking of. Now, if this initial velocity is starting from rest, it would go to 0, and which is many times the case. Okay, again, if it's not specifically stated, that's usually the assumption that we make. Okay, just so that you know. All right. So let's go back using those two. Oh, before we move on, units of acceleration. Do you guys know what the units are for acceleration? What would we be expecting for the units of acceleration? Do you guys know? Say that again. Yes, distance over time squared. So many times we hear it in terms of inches per second squared, feet per second squared, millimeters per second squared, meters per second squared, right? So distance divided by, and it would be over time squared. So let's look at an example and let's work this one together. So in example 7.1, the problem statement is on page 171, says determine the acceleration and the displacement during a 3-second speed up described in the problem. Okay. And then we're just going to go through this process. What are the variables that we use? Or what variables do we know? What variables do we need? What equations are available to us to use? And then, you know, kind of list your plan or your steps that you're planning on taking. So I'm going to go underneath and we're going to look at example problem 7.1. Over a little bit. So it's on page 171. And it says here that an express elevator used in tall buildings can reach a full speed of 15 miles per hour in 3 seconds. It's pretty fast. Assuming that the elevator experiences constant acceleration, determine the acceleration and displacement during the 3-second interval. Okay. So as we look here, we want to first identify what are the variables that we know in this problem. Okay, so if we look at this problem statement, we have 15 miles per hour. Okay, so this is going to be example 7.1, and this is our first practice problem. So when we look here, we've got 15 miles per hour. What variable would that be? It would be a velocity, okay? And Christian, you said it's probably going to be the ending velocity. Most often we refer to that as final velocity or VF, okay? So VF is going to be 15 miles per hour. What is the 3 seconds? What variable is the 3 seconds? That would be what? That would be time, or it's sometimes referred to as change in time. Oopsie. Because we're speeding up, if you would, to 15 miles per hour, and it takes us 3 seconds to do that, right? So that would be a change in time from our start to our finish. Okay. So those are the two variables that we have. What do we need to try to find in this problem? What are the things that are unknown to us, or the things that they want us to figure out? I heard something in the back. I just couldn't hear it. Acceleration. Okay, so A, right? And displacement or that distance, right? Good. Right. So those are the two things. Now, we had just looked at two equations, right? So we looked at the bottom of page 170, acceleration is equal to change in time over velocity. We have a velocity, we have a change in time, and we have to find an acceleration. So that one's probably going to come in handy. And then we also have this distance one, okay? Now it needs an acceleration. So it looks like we probably have to calculate our acceleration first, right? So if we look here, acceleration, I'll kind of call this part A. Acceleration is going to be equal to, and I'm going to use that equation 7.3, change in velocity over change in time. Expanding out the change in velocity, it would be the velocity final minus the velocity initial. Okay, I just use F and I for each of those. divided by the change in time. So remember, you're always writing out for me your equation in variable form before you put anything in. Don't start putting any numbers or units or anything in. Write out your equation in variable form first. And then we're going to line up the elements. Now, you'll notice that our velocity final, because we're going, it says here that we're speeding up, to 15 miles per hour in 3 seconds. That would be our velocity final, right? As we identified. And then we have our time in seconds. So right now, this is in miles per hour, and this is in seconds. So if I would put 15 miles per hour minus 0, because that would be my initial velocity, assuming we're starting from rest, our final velocity there. And I would put in here 3 seconds. Notice that I'm have miles per hour per second, which isn't great units. We want to have the units kind of be consistent. So we're not going to use 15 miles per hour here. We're going to have to convert it. And if we peek ahead at the end, kind of towards the bottom, they're going to want us to find distance in feet, okay? And since we have this in seconds, what we're going to do is we're going to convert our final velocity to be consistent with those units. So we're going to convert miles per hour to feet per second. So over on the side here, I'm going to do that. So my velocity final is equal to 15. And remember, when we have like MPF or our RPMs, we want to expand out those units so that they're top bottom. So in this case, it's going to be 15 miles per hour. And we want to get to feet per second. So I'm going to get my miles into feet. Does anybody know how many feet are in a mile? 5,280, correct. And that's going to be 5,280 feet in 1 mile. And then I want to get my hours into seconds. So I know that in 1 hour, there's 3,600 seconds. So my hours will cancel. So my units that are not canceled are feet on top and seconds on the bottom. So feet per second. So I'm going to multiply across the top and I'm going to divide by the bottom. What do you guys get for a value for your final velocity? What do you get for your final velocity? 22, right? 22 feet per second. Yes, 22 feet per second. So this value, okay, in its converted form is now going to go up into here, okay? So if I look at acceleration, that's going to be equal to 22 feet per second minus the initial velocity, which as we stated, because we're an elevator, we're assuming that's 0. It doesn't say the initial velocity is 0. It doesn't even say we're starting from rest, but based on the problem, that's a good assumption to make. And then divided by the time it takes us to go from 0 to 15 miles per hour or 0 to 22 feet per second, it's going to be 3 seconds. And this now, Christian, you were ahead of me. This is the acceleration, not the velocity, right? And what did you get for that value? 7.33. And what are the units? Feet per second squared, exactly. So this is going to be feet per second squared. Are there any questions on the units? Because this is feet per second per second. So those per seconds, they combine on the bottom and they end up being feet per second squared. Okay. So I can put a box around this. This is one of the answers that it asked me for because it wanted to know what is the acceleration that we're experiencing when we change from rest to 15 miles per hour in 3 seconds. Okay. Then we've got the second part here is during that same interval, experiencing that acceleration, what is the distance that we cover? So at the top of page 171, the equation is going to be 1/2 times the acceleration that we just calculated times the time squared plus velocity initial times the time. So We're going to write our equation out in variable form first. D is equal to 1/2 AT squared minus plus velocity initial times the change in time. Now, because we're assuming our velocity initial is 0, 0 times whatever time, the 3 seconds is still going to be 0. So the ending part here is going to go to 0. So we're just going to plug in values for the 1/2 times the acceleration. Acceleration that we just calculated in the step above is going to be 7.33 feet per second squared. And then multiply by the time that it takes us, which is that 3 seconds, and we're going to square that value. Don't forget to square that. It's so easy to forget that square. So you're basically going to take 9 times 7.3 times 0.5. And what do you get for this? 32.9? That's what I get. Now, units. We're expecting feet, right? We're expecting feet, but let's make sure that it comes out. So when we square this value inside of here, this becomes seconds squared. And if you would, over 1, because it's a whole number. So this second squared is going to cancel out the second squared in the denominator of the acceleration. So we are left with just feet. So this would be 32 feet. So we're covering a distance of 32.9 feet in 3 seconds when we have a constant acceleration of 7.33 feet each second, feet per second each second, sorry. Okay. Any questions on example number 1? Make sure, again, I'm going to point out a couple things. Number 1, I have to be able to read this. Also, label that this is example 1. Sometimes I get problems in and somebody just starts writing. I'm like, what is this for? And I've got to kind of line it up. So let me know what you're doing, what the example is. Make sure that you have units in all phases of the problem. I don't want them to magically appear. Part of this is making sure that you resolve your units because, as I've stated over and over again, we end up with the correct units that we're expecting and it all, cancels or doesn't cancel, there's a great chance that you have it set up correctly, or then you need to troubleshoot and figure out what went wrong. Okay, so that's our first practice problem. So put that aside and make sure that you can reference it and pull it up when we need to. So I'm going to move this out of the way. We're going to go back to our PowerPoint presentation. We went through that process. Now let's talk about acceleration, just of a general point. So acceleration, when it is pivoting around a single fixed point, when we have a single link, if you would, rotating around a fixed point, it's going to have 2 components of acceleration. Those 2 components of acceleration are going to be a tangent component and a normal component. Now, the tangent component, its direction will always be perpendicular to the center of rotation in the direction of acceleration. So this is where we go back to, if we're accelerating, if we're speeding up, then our tangential component will go in the same direction as the velocity, okay? If we're slowing down, the tangent component is going to go opposite the direction of velocity. So when we're decelerating, our acceleration is going the opposite direction of what the actual motion is, okay? So we can still be moving forward, but we're slowing down, okay? Now, the normal component is 90 degrees to the tangential, and it's always going to point towards the center of rotation. Always, 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 always. Okay, that one's kind of easy to remember, if you would. So those are the 2 components that we're going to be looking at. So if we turn the page and we go to page 173, okay, we see this in figure 7.2 right here. Okay, right here. I want to make sure everybody's following along. If you're writing, I don't want to go further until you're ready. So if we look at point A here, point A, you're going to notice, has a path of movement and it's an arc. So that means that it's rotating about a fixed center. Okay. So its motion is going around in a circle. Now, we know that there is a straight line velocity component, as we learned and applied back in our previous module, module 3, chapter 6, that there is a straight line velocity component. Okay. And we saw how that related to angular velocity of the link. So it always is going to be perpendicular to its center of rotation. So if this is moving around, its center of rotation is down here somewhere. So it's perpendicular to that. And it's also in the direction of rotation. So if this whole link is rotating around, it has to be going in a clockwise direction because the straight line velocity component, shows us that that's the way that it's going. Okay. Now, acceleration, those two components that we talked about, the tangential component is going to be, if this is the radius back to the center of rotation, it's going to be perpendicular to that radius back to the center of rotation. And it is going to be in the direction of velocity when we are speeding up. So right now, the way that this is drawn doesn't tell me, but I can see that it's speeding up because acceleration is in the same direction as the motion. Okay. If it was going in the opposite direction, which it can still be perpendicular to that radius back to the center of rotation. It just means then we're slowing down. Okay. The motion is still going, the way that the velocity is, but we're just getting, slower and slower as time goes by. Now, the other component of acceleration is going to be the normal component. The normal component is going to be perpendicular, if you would, to that tangential, but it's always going to point from the point of, if you would, application, or the point that we're looking at, towards its center of rotation. Always. It's never pointing out, ever. This is the force that's holding it in a circular path. So that's what it is. Or I shouldn't say the force, but it's the acceleration that's holding it there. Okay. It's also the, well, we'll talk about that a little bit later. It'll be coming in a little bit. Okay. Now let's look at calculating this value. Okay. Oh, sorry. I think we calculate those a little bit later. Sorry. So now that we're going around a point, okay, before we talk about the tangent, the specifics of calculating tangent and normal accelerations, that's where I was going. The book wants us to first look at angular acceleration. Now, we had angular velocity. Angular velocity was when we were looking at a link that was rotating about a fixed center, and that entire link had a rotational velocity in terms of one of two things, either revolutions per minute or radians per second. Okay. And what that told us was how fast that link was rotating. And every point on that link had the very same angular velocity. Okay. Now, in these terms, we're looking at angular acceleration. So now we're looking at that angular velocity and we're wondering, how much is it speeding up or slowing down? So it's just that change in angular velocity now. So instead of a straight line motion, we're looking at things that are rotating. So angular acceleration is the acceleration when we're trying to find out how much angular velocity is changing. So in equation 7.9 right here, you're going to notice that angular acceleration is equal to the change in W, which is the change in angular velocity, divided by how much time it takes. Now, something I want you to notice, okay, is we are going to see that there's a difference here. Lowercase a is equal to straight line, traditional, if you would, acceleration, okay? This cursive a, this is actually alpha, okay? It's kind of like I look at it, it looks kind of like a fish, if you would. Alpha is angular acceleration. So sometimes when we look at this, it looks like a regular lowercase a. It's not. This is alpha, and it is angular acceleration. And then the regular lowercase a is going to be regular straight line acceleration. Okay, so it's kind of like trying to determine, as we do more problems, you'll see that difference, but I wanted to point that out here. And then this is the equation for angular acceleration. Now, when we look at units for angular acceleration, they are going to be, and they show them down here in this paragraph. They can be one of three things: degrees per second squared, revolutions per second squared, or the preferred units are going to be radians per second squared. Okay. And that's where we usually get them. Okay. And we calculate them to be that value. All right. We don't convert on acceleration because honestly, acceleration doesn't mean much to anybody else when we're trying to, if you would, specify things. So if I was buying a motor, I wouldn't try to specify for them, I want a motor with an acceleration of blah, blah, blah radians per second squared. I'm just going to give them how many RPMs do I want? That's it. And that's going to be our angular velocity. So in terms of angular acceleration, we don't do any converting usually after we get this in radians per second squared. We just leave it. Okay. Or use it wherever we need to. Now, when we want to start looking at, if you would, angular distance, or just looking at angular displacement in terms of either revolutions or degrees, we can determine how much we have rotated, like I said, in revolutions or degrees, by using a very similar equation to straight line distance under acceleration. So in this case, we're going to use 1/2 times angular acceleration. So notice the alpha there instead of the lowercase a, times the change in time that it's taking us to do this, squared, plus any initial angular velocity times that same time. Okay. So this looks very similar, like I said, except when we're rotating, we're now trying to find what are the degrees that we've either gone through or number of revolutions. And then we're using the angular acceleration rather than straight line acceleration. Okay. Let's look at another example. Example 7.3. Example 7.3 is at the top of the following page, 174. And we have an electric motor. It drives a grinding wheel right here, clockwise. Okay, so you're going to notice our W is going in a clockwise direction as shown. It will speed up to 1800 RPMs in 2 seconds. Okay, so notice next to it, there's another arrow that is going clockwise, and it has alpha next to it. Okay. Now, because this says it's speeding up, notice that alpha angular acceleration is going in the same direction as angular velocity or the rotational velocity. All right. So when the power is turned on, so assume that it's speeding up at a constant rate, determine the angular acceleration. So that's going to be alpha. Okay, we're going to be calculating alpha of that grinding wheel, but also determine the number of revolutions that wheel spins before it gets up to full speed. So how many full revolutions is it going to take to get to 1800 RPM in that 2 seconds? Okay, so as we look here, you're going to notice that we want to find alpha and we want to find the change in, if you would, angular displacement. That's what theta is just kind of referring to, if you would, an angle. So the two equations that we have were on the previous page that we were here. So the first one was 7.9. Alpha, or angular velocity, is going to be equal to change in rotational speed divided by time. And then the other equation that we're going to use is going to be right here. So this is example 7.3. Okay. All right, so starting out, I always like to write out, what do I already know? Okay, so this is example 7.3. So as I read here, I see that I have a number. I have 1800 RPMs. What variable is 1800 RPMs? I'm going to ask virtually, what's 1800 RPMs? What variable would that be? Would it be A? Would it be alpha? Would it be W? Yep, final W. Thank you, Lex. So angular velocity final. So we're going from nothing and we're speeding up to, thank you, Jack, as well. It's going to be equal to 1800 RPMs. Then we've got 2 seconds. That one's always easy, right? That's going to be the amount of time or the change in time that it takes to, go from rest, if you would, to 1800 RPMs to speed up. Okay. So now we want to calculate what is our alpha. Okay. So we want to find alpha, and we also want to find our angular displacement. Okay. And then in this case, they're asking us to get that in RP or in revolutions. So we'll start with the angular acceleration because we're going to need that for the other equations. So angular acceleration is going to be our part A. It's going to be equal to, might have to look back if you need to. That's going to be on the previous page, the change in angular velocity divided by the change in time. So change in angular velocity divided by change in time. Expanding out the change in angular velocity, it's going to be the angular velocity final minus initial divided by change in time. And as we stated, our assumption here is going to be that our initial is starting at 0. So our final is going to be the 1800 RPMs. Now, just like in our other equations, we cannot use RPMs in and out of this equation. We have to use our radians, if you would, per second squared. So we need to convert our final, our WF, to radians per second squared. I'm sorry, 2 radians per second. Our angular acceleration will be radians per second squared. So we're going to take 1800 revolutions per minute, and we're going to convert that to radians per second. So go ahead and do that. So you should get 188.5 radians per second. Okay, make sure you can get that. Then we're going to use that value up here. Okay, so our alpha is going to be equal to 188.5 radians per second divided by the 2 seconds that it took us to get there. Okay. So now you're going to notice we're going to have radians per second, or radians per second squared, which are the correct units. We don't cancel anything out here. The second squared combines on the bottom. So our alpha, what do we get for alpha? 94.25. I got 94.4. So depending on what you rounded. So 94.4. I'm going to stick with that. Radians per second squared. And that's one of the values that they were asking for. They were asking for what is the angular velocity. So that was one of our unknowns. Okay. Now our part B, we want to figure out, okay, how many revolutions did it take us to go from rest to that 1800 RPMs using constant acceleration that we see here? We want to know what this is. Okay. So what is our angular displacement? So if we go back a page at the bottom here, oopsie, yep, at the very bottom here, further, equation 711, 1/2 angular acceleration times the time squared plus initial angular velocity times the time is our equation. So we'll write that out. And now using that angular acceleration from above, that's going to go right there. Let's calculate how much displacement we're going to get. Now I just want to talk about units for a second, okay? You're going to notice that in the denominator of your units for acceleration, 94.4 radians per second squared, when you multiply that by the 2 seconds squared, these units inside go to squared, right? When we square that quantity. So the squared cancels out the squared here. So in this case, we're left with just radians, all right? So you should get 188.8 radians left over, right? Do you guys get that value? Now the problem says that we want to know it in revolutions, which does make sense because kind of makes it, you can relate more to, yeah, well, we care about radians, right? But they're not relatable, right? They don't like, you can't feel it. But revolutions, you have a better idea of what that means. So we want to convert this final answer then to revolutions. So we're going to go 2 pi radians in 1 revolution. Okay, radians cancel out. So our change in angular displacement is going to be 30 revolutions. Did you guys get that same value? Or very close to it? Okay. So any questions about the second practice problem? Okay. All right. Now, we have been kind of paging back and forth, trying to get all of our equations, you know, like which one do we use and such. So what I want us to do here, and this is part of your practice problems as well, you're going to be handing in for me an equation sheet, okay? Now, I'm going to kind of give you a peek at the one that we're going to be creating, at least today, but we'll be adding a little bit to it. So we're going to start at the top here. We're going to identify our velocity equations, our acceleration equations, and then components of acceleration. And I'm still going to have a little bit left down here, okay? So where we're going to start is we're going to start with this portion right here. We're going to put the equations on the left-hand side, and then we're going to put the variables that match up. So the only reason I want you to show you this is because I want you to have enough room to kind of write everything, okay? So if you spill over into a second sheet, it's totally fine, but we've got like stuff to write on here. All right, so let's start with our velocity equations. And this is really a review from our previous module. So again, you're going to be handing in this equation sheet with your practice problems. I want to make sure that you have one and that it's, you know, that it's correct. So our first set of equations here is going to be velocity equations. Okay. And kind of down the middle, the left-hand side is going to be my equations. My right-hand side is going to be what the variables are with units, okay, that we would expect. So the first velocity equation, straight line velocity, is simply going to be velocity is equal to distance over time, okay? So our little straight line velocity v, I always put a little tail on mine, only because there are other quantities like volume that you could mistaken the v for. And a lot of times we see it in italics, so it has that little tail, that little like wing on the end. So this is going to be straight line velocity. Okay. And the units for that, what was that? Sure, you can write linear velocity. The units for that are going to be inches per second, right? And straight line velocity will always be in distance over time. So I'm just using an example. If you wanted to put in feet per second or millimeters per second, you know, something like that, just put a set of units here because then it just kind of cues you in on what you're expecting. Okay. D is going to be equal to distance, which we would be expecting if we're using kind of those same units, inches, feet, meters would be appropriate for it. And then T is equal to time, which seconds, minutes, hours would be appropriate for that. Now, another equation that we see for straight line velocity when we're on a single link that's rotating about a fixed center is angular velocity. It's going to be equal to straight line velocity over the radius. Or V is equal to WR is another form, right? Just rearranged. So in this case, our straight line velocity is still the same. Our distance is now going to be a radius, but we would still have units of distance for it. Okay, it's just that now it's a radius from a center of rotation to a point that's rotating. All right, and then our W, or a lowercase omega, is going to be angular velocity. Let's forget that I. Velocity. And units there are either going to be in RPMs given or radians per second, right? Or we convert to radians per second in and out of that equation. I'm going to put that note there. Always radians per second. And then we had the relative velocity vector equation. So relative velocity, and that's going to be the velocity of an unknown. It's going to be equal to the velocity of a known plus vectorially the unknown relative to the known. Okay. And that's just that vector equation for reference. Okay. I'm going to put a cloud around. So any question on velocities right now? All right. Then let's look at acceleration equations. Okay. We know straight line acceleration, lowercase a, not alpha, it's going to be equal to straight line velocity. I'm sorry, yeah, the change in straight line velocity divided by the change in time. If we expand out our delta V, it's going to be V final minus V initial divided by that change in time, or the time that it takes us to do that. So over on the right-hand side, when we expand that out, VF is going to be velocity final, or final velocity, whichever. Okay. And units there are inches per second. Okay. Then VI is velocity initial. And that also is going to have inches per second. And then change in time is the same as above. Distance is the same as above. Well, I don't have distance yet. I will get distance in just a bit. Okay. So I'm not going to repeat the T because time is the same for all of them. Now, we looked at distance. Straight line distance covered when we're accelerating is going to be 1/2 AT squared plus initial velocity, if there is one, times the change in time. So distance here is the same as it was above, so I'm not going to rewrite that variable. So even though distance is up here, it's the same. Okay. Oh, I need to put acceleration, A. A is equal to acceleration. And you could say linear, right? Probably a good idea to actually put linear in there. I'm actually going to do that. Linear acceleration, because we don't want to confuse it with the angular acceleration. So linear acceleration. And units for that are going to be inches per second squared. If we're kind of sticking with the inches per second for velocities, right? Any questions so far? Makes sense? And again, we're just trying to get everything kind of in the same place so we're not paging all the time when we're trying to, figure out what we're going to use. So the next one's going to be angular acceleration. Okay, so it's going to be alpha. It's going to be equal to the change in angular velocity divided by the change in time. So the change in is that triangle or delta, which expanded out, it's going to be the final angular velocity minus the initial angular velocity divided by that change in time. So over here, we're going to have a W final, which is going to be angular velocity final. Okay. And that is going to probably be given to us in RPMs, but we're going to have to use radians per second in this equation here. So W in that equation needs to be in radians per second. And then initial, angular velocity initial, and it has the same RPMs or radians per second. And then alpha, should put that in here, that's going to be angular acceleration, and its units are radians per second squared, or revolutions per second squared, or degrees per second squared. But this one is the most accepted and common coming in and out of that equation. And then lastly, angular displacement. So change in angular or angle, change in angle, it's going to be 1/2 angular acceleration times the change in time squared plus angular velocity initial times the change in time. And here, change in theta is angular displacement. Now, its units can be revolutions or radians, okay? And we'll get radians out of that equation, but then we change it to revolutions to kind of be able to relate to it a little bit better, okay? All right, so that's where we've kind of, been so far. Any questions? All right, we are going to be adding some more down here. I'm about a little bit over half down my paper. If you end up going further, it's totally fine, but we've got a little bit more to go. So we're going to leave that as is for right now. We're going to go back to our PowerPoint presentation, and I'm just going to catch us up to where we are at. So we did acceleration of a link. We did equation 7-9 units for angular acceleration. We then did example 7-3. Okay, so we did this one together already. So we've already gotten all the way over here. So now looking at section 7-4, we're going to talk more in detail about angular and tangential acceleration. So the normal component of acceleration is created as a result of that change in direction. So the acceleration normal component is due to changing the direction of the velocity. So when we're rotating about a link, it's the normal component of the acceleration that's pointing back towards the center of rotation, kind of keeping it in a circular path, okay? The tangential component is going to be formed as a result of the change in the magnitude of the velocity. So that's our speeding up or slowing down, okay? And that's going to be tangent to the radius back to the center of rotation, either in the direction of velocity or opposite, Now let's look at tangential acceleration. So we already talked about its direction. To calculate its magnitude, we are going to use the top of page 175, okay, right up here. And how we denote it is it's going to be acceleration, lowercase a, and this is going to be the tangential component. So it's going to be a, what kind of a script do you call that? A subscript? A superscript. Superscript is high, right? So the superscript is going to be the t, and the subscript is going to be the point at which we're referencing. So in our kinematic diagram, it's going to be the letters. It's going to be the A, the B, the C, the D, okay? So in this case, they're looking, I guess, at a point A. It's the tangential component of acceleration for point A. And we're going to go all the way to the end here, and it's simply going to be the radius or the distance away from the center of rotation that that point is times its angular acceleration. It's real easy, okay? Not hard to calculate at all. And then the magnitude of the normal component can be one of two arrangements. It can either be the angular velocity squared times its distance from the center of rotation, or its r, or it can be the straight line velocity component on that point divided by the distance away from the center of rotation. Okay, so either one of these can be used depending on the information that you're given. So what we're going to do is we're going to add those back to our equation sheet. Oh, it's underneath here, my equation sheet. So let's add these two to our equation sheet. So I'm going to add a section here, components of acceleration. Okay, and I have two of them. My first one is going to be the tangential acceleration is going to be equal to my radius or my distance away from the center of rotation times alpha or the angular acceleration. So AT is going to be the tangential component of acceleration. Okay. Now, since it's a component of acceleration, get this out of the way here. Since it's a component of acceleration, it's going to have the same units as angular or as regular acceleration. Sorry, this is the component of the straight line acceleration. So we go back up to linear acceleration. Our units are going to be inches per second squared. Okay. And then we want to say this is going to be perpendicular to the radius of rotation, okay? And as we know, it's either going to be pointing in the same direction as velocity if it's speeding up, or opposite the direction of velocity if it's slowing down. Now, our other component of acceleration is going to be the normal component of acceleration. And that can be either angular velocity squared times its distance from the center of rotation, or the velocity of that point squared, straight line velocity of that point squared, divided by its radius back to the center of rotation. So radiuses are above already, W's are aboves, V's are aboves, alpha is above. So we just need to add the normal component of acceleration. It as well is going to have units of inches per second squared. And its direction is always going to point towards the center of rotation. You guys read that? Point towards the center of rotation. That's the normal component. So that goes back to figure 7.2, where the tangential component perpendicular to center of rotation, or the radius back to the rotation, and then you can see that the normal is pointing back towards the center of rotation. Always, always, always. All right. Now we have one last thing to add here, and that's the total acceleration. So since there are two components of acceleration and they're 90 degrees to one another, let's say I want to know what the total acceleration is, okay? And we call that a capital T is a sub capital T. So it's the total acceleration. And I'm going to write this out here and I'm going to see if it makes sense to you guys. We're going to take the tangential component, we're going to square it. We're going to add the normal component and we're going to square that. And we're going to then take the square root. Does that sound familiar? Does it look familiar? It's Pythagorean's theorem, right? Oh, Lex had a question. She says, can theta be in degrees like 40? Yes, it can. Yeah, it can. Many times it can either be in, I thought I put it up there. So it can be revolutions or, oh, it could be or degrees. Yes, you could say or degrees. Sorry, I didn't catch that when you did it. It's been a couple minutes. All right. So my total acceleration, getting back to here, because our tangential and our normal are 90 degrees to one another, I'm gonna go back here, okay? If I take and I go through the endpoint of my tangential, through the endpoint of my normal, and I go back from that origin, here is the resultant total acceleration. So we use Pythagorean's theorem to get the magnitude. And you can imagine that we'll use CAD then to get the angle that it's at, because it's going to change depending on, you know, where that link is in space at that moment. Okay. So that is our total acceleration. So I'm just going to put AT is equal to total acceleration. Okay. And that as well is going to have the same units as above, inches per second squared. Okay. Okay, we have one more example that we're going to do tonight. And that is going to be example problem 7.4, and it starts at the bottom of page 175. 175, so it's right down here. Okay. So example 7.4 says we have a mechanism shown in figure 7.5. It's on the following page. Okay. So if I go over here and I look at the top of page 176, here's the mechanism that we're interested in right here. Okay. And we're actually going to focus on, you know, just one portion of it, but we'll get there in just a bit. So it says it pushes boxes along a platform and to a loading area. The input link is driven by an electric motor, which at this instant shown has a velocity of 25 radians per second and accelerates at a rate of 500 radians per second squared. How nice that they have our things already in the units that we need them in. Knowing that the input link has a length of 250 millimeters, determine the instantaneous acceleration of the end of the input link in the position shown. Okay, so let's kind of look at what we have here. Okay, so I'm going to get out a piece of paper. Okay, so this is going to be example problem 7.4. I kind of move out here and bring my book back and forth, I think. So this is example 7.4. All right. And now what we want to do is we want to kind of take what we have there and look at what is given and what are we trying to find. So I guess maybe start with what we're trying to find. We're trying to find, it says instantaneous acceleration. So that means that it's going to be our linear acceleration. So we want to know what is the total acceleration. Okay, so when it just says acceleration, remember, it's going to have two components. It's going to have normal and tangential. So if it's just asking for acceleration, what is the total acceleration due to those two components? So it's going to be the total acceleration, okay, at the end of that link in that position. So go back to the diagram. So here is the input link right here, all right? And so they drew the kinematic diagram as we see it right here. I'm not going to draw that today. We're going to point at some things in the end, and we'll get plenty of practice to draw kinematic diagrams and put these things in place. But for right now, we're just gonna kind of point to what they have here. So they've got their kinematic diagram, and they're focusing just on this input link right here. And what they're referring to is they want to know, what is the total acceleration of point A? What is AT? What is A total of point A? And they're telling us that, and they gave this to us in the problem, our angular velocity is 25 radians per second. Now, in the problem itself, I want to point this out. They said that the velocity is 25 radians per second. That doesn't mean V. So be careful. Look at the units here. This is why it's important that you know the units you're expecting. So they're saying that that link has a velocity of, actually angular velocity, if they want to be more specific, because of the units that are given. If it was regular straight line velocity, this would be in like inches per second, feet per second, millimeters per second, okay? But it's not. It's in radians per second. So if we go back to our equation sheet, radians per second goes along with angular velocity. So we're given an angular velocity, all right? So at this instant in time, our W, okay, so our angular velocity of link number, what's going to be link number 2, sorry, kind of underneath here. It's going to be link number 2 is going to be 25 radians per second. Then the other one that we have here in the problem statement, it says the acceleration, it accelerates at a rate of 500 radians per second squared. That is not straight line acceleration. This is angular acceleration because of the units. If we look back at our equation sheet, angular acceleration, it's the alpha, not the lowercase a. So be careful. Alpha is radians per second squared. So that's angular acceleration. So this is alpha. Is equal to 500 radians per second squared. And then lastly, we have a radius. It says here that the length of that input link, so from the center of rotation, from the center of rotation out to that end point is 250 millimeters, okay? So we would say R, because it's a radius of rotation, is 250 millimeters. All right, now, since we need to find the total acceleration, right? We know that from our equation sheet, the total acceleration is going to be equal to, using Pythagorean's theorem, using the tangential and the normal components, right? So we can say that AT is equal to the square root of AT squared, and that's going to be of point A, because that's that point on the end of our link that link number 2, plus the normal component of that same point squared, and then we're going to square root that addition. Now, as we look here, we're not given tangential values, are we? So we've got to look back at our equation sheet. How do I find the tangential acceleration and the normal acceleration? Using, hopefully, variables that were given. So our tangential is going to be the radius to that point times the angular acceleration. Cool. we are given angular acceleration. This would be of link number 2, and this would be the radius of link number 2. So we can say the tangential out to point A is going to be equal to alpha 2 times the radius of 2. So that one we'll be able to kind of plug and chug and put that in. The normal at point A, we bring this back. We've got two versions of it, either using the angular velocity of the link or the straight line velocity. And if we look here, this is where it's important to know what you have. And based on the units, we identified that 25 radians per second is angular velocity. So we will be using the angular velocity of link number 2 squared times the radius number 2. And I put it in parentheses because we're using link number 2 and we're squaring it. I don't want to get confused with things. Okay, so we're going to calculate these two first to get the total, then acceleration. Okay, so step A or part A, if you would. There's nothing right now to draw. We would be drawing this kinematic diagram, as you can imagine, in AutoCAD, and then we'll look at directions once we get done with our magnitudes here. Okay, so let's calculate that tangential at point A using alpha 2 times the radius 2. So we're just going to plug and chug directly. So this is going to be 500 radians per second squared times the radius of 250 millimeters. So my acceleration tangential component, its value will be multiplying those two out. Sorry. So you should get 125,000. Now, radians times millimeters is going to be millimeters, right? Per second squared. So millimeters per second squared. Now, what the book does in here, and this is kind of a judgment call. We could end it right here and keep this in millimeters, but they converted to meters just so they wouldn't have all the zeros to deal with. Okay. So all they did is they said 1,000 millimeters in 1 meter. Okay. So our tangential at A is 125 even meters per second squared. Okay. And again, just to not have to deal with all the zeros because it's such a big number. All right. So this is, we're going to be using that for the total a little bit later. So that's our tangential component. Now we want to do our normal component. So the normal at A is going to be equal to our W2 squared times radius of link number 2, or the length of link number 2. So that's going to be, if we look back up here, they gave us the angular velocity of link number 2 at 25 radians per second. Now we have to square that 25 and the radians per second, okay? Times the radius of 250 millimeters, okay? So our normal at A should come out to be 156,250 millimeters per second squared. Okay. Now, this is where you have to be sure that you square the 25 because that comes out to be like 600 and something, 625. Then you multiply that by 250. Okay. What also happens are the units underneath here square. So it's going to be radians squared over seconds squared. When we take radians squared times millimeters, what do we get? Just millimeters, right? Just millimeters, but it's per second squared. So that's where the per second squared comes in. And that's consistent with the type of units that we would be expecting. And then all they do is they divide by 1,000 millimeters to change this into meters. So our normal component at A is going to be 156.25 meters per second squared. So magnitude-wise, any question on the tangential and the normal components? Okay, and so those are going to be, if you would, I'm going to go to this example. This is where I'm talking about that I'm kind of pointing at. So the tangential is going to go in the direction of rotation because it's speeding up. So we know that our angular velocity and our angular acceleration are both going clockwise. So that component, that acceleration component, the acceleration tangential component at A is going to be perpendicular to its radius of rotation, okay, in the direction of angular acceleration. Then from A, the normal component of acceleration is going to point back towards the center of rotation. Always, always, always. Now, that's where they would be along the link. So we would draw this if you would. This would be your CAD work, okay? And we would draw that along the link, for instance. And again, you're going to get plenty of practice to do that. Don't worry. Now, total acceleration, because we have two components of acceleration here that are 90 degrees to each other, this is where our total acceleration is going to be the resultant of those two. So now we're going to use that Pythagorean theorem's version of acceleration using those two components. So part B here is going to be, our acceleration total is going to be equal to the square root of the tangential at A squared plus the normal at A squared, or in either order, honestly. So we're going to put underneath the radical 125 meters per second squared plus 156.25 meters per second squared. And our acceleration total. 200.1. I got 199.9. Or you know what we're going to say? We're going to say 200 meters per second squared, because we're going to square it underneath here, but then we're going to take the square root and it goes back to its meters per second squared. Okay. So approximately really darn close to 200. I got 19 or 199.9. You got 200.1. Is that right? Yeah. 200.1. 200.1 is what the book got. Yep. We're talking, acceleration's pretty darn close. Now, that's the total acceleration. Direction-wise, that's its magnitude. Direction-wise, then, as we said earlier, is going to be the vector sum or the resultant of adding those two together. So you can either do it as a vector sum like we see here, kind of like components and finding that resultant, or you can use a vector triangle where you take the normal plus the tangential and then back to the origin, and then we would show the resultant going from the origin and pointing to that last vector. Okay, either way, and then these would be 90 degrees to one another. Okay, so no CAD work here, no direction stuff for this example. I just wanted to kind of get us warmed up to the equations and units and showing your work. So for example 7.4, I'm going to zoom out here a little bit. We would start with, make sure that you tell me it's this example. We are not, don't worry about a diagram for this because we referenced the one in the book. We didn't draw it here. I just want you to see the work. So I want you to always show me what you know, what you're trying to find, and then what are the equations that are going to apply, and then do the work down below, combining and canceling all the units, as needed so I can follow it along. Okay. So right now, any questions at all? Okay, so practice problems wise for the very first start here, that should be what we need. Let's get ourselves caught up on our PowerPoint presentation. So we did tangential acceleration, normal acceleration, total acceleration, and we did this last example. So this last slide says next time we're going to be building on this and we're going to be looking at relative acceleration method. We're going to find there's going to be some parallels to how we did things in velocity, but Now it's going to be in terms of acceleration. So it's just like more, more. There's more stuff. And we're going to be focusing on, adding acceleration then to the 4-bar mechanism velocity work that we did in module 3. So for right now, that's as far as I'm going to go today. The next time that we get together, we'll be looking at part 2. Okay. So we're not going to worry about an exit slip. I didn't make one up. But let's take a peek at assignment number 4. Okay. I want to see if there's anything that you guys could start looking at the end here of chapter 7. So everything is in chapter 7. Okay. So if we look here, we've got, look at the wrong ones. Let me just circle the ones here. We've got 7-2, 7-6, 7-8, 7-16, 7-18. And then I think 26. Yeah. So those first ones. So it looks like about half of these. So 18 and above, you should be able to do. So let's take a peek at those underneath the camera here. So on page 206 starts the problems for chapter 7. So number 2 says a high performance vehicle has a 0 to 60 miles per hour in a time of 8.3 seconds. Determine the linear acceleration of the vehicle and the distance traveled in reaching 60 miles per hour. Okay, 60 miles per hour. What I don't want you to do is when you do this, I don't want acceleration expressed in miles per hour per second. Okay, put it in like feet per second squared, that kind of thing. Does that make sense? Yeah, because it doesn't feel right to do it like that. Don't do the acceleration in miles per hour per second squared, I should say, per second squared. Okay. No, miles per hour is per second. No, that's right. Do it in consistent units underneath where you would get a square. So for instance, feet per second squared, inches per second squared, that kind of thing. Okay. The next one, 7-6, starting from rest. A cam accelerates uniformly to 750 RPMs clockwise in 8 seconds. Determine the angular acceleration of that cam. Okay. Number 8, the angular velocity of a shaft is increased with constant acceleration from 1000 RPMs to 250 RPMs clockwise in 20 seconds. Determine the angular acceleration of the shaft. Looks like we have an initial angular velocity and a final this time. So instead of putting your initial to 0, there's going to be a value here. Okay. Your next one is going to be number 16, it looks like. This is going to be normal and tangential acceleration. So link number 2 is isolated from a kinematic diagram and is shown in figure P716, which is at the top of the following page. So this is the illustration that they're referencing. Okay. The link is rotating counterclockwise at a constant rate of 300 RPM. Determine the linear acceleration of points A and B, and then use the angles so that, A and B, so that you can see them up there. Then your next one is going to be 18. And it says that link number 2 is isolated in the kinematic diagram. Up here, same illustration. Okay. The link is rotating counterclockwise at a rate of 300 RPM and is decelerating at 800 radians per second squared. Determine the total linear acceleration of points A and B. Okay. Use then those angles as reference. All right. And then after that is going to be work that we're going to do the next time. So you certainly can get started on the homework tonight. Okay. Nobody go anywhere because I took attendance, but I want to be sure that I have everybody because there was a couple people that snuck in towards the end. And what I'm going to do now is I am going to stop our recording